Okay, welcome to this screencast on divisibility in prime numbers, which is chapter 2 of our option topic, Discrete Mathematics. And we're going to start off in section 2a, which deals with factors, multiples, and remainders, which seems a little sort of babyish, doesn't it? We're doing higher level maths here, and these are some fairly elementary concepts, but as you'll find out, there's some proofs and there's some catchy bits. So there's a little bit to learn, a little bit to pick up. So we will look at some fairly familiar concepts, but we'll also probably look at doing some things that you're not so familiar with, and also some awkward, kind of clunky areas that we have to get a little bit more comfortable with. Anyway, let's fire into it. There's a bit of notation involved in this area. So let's start off with that. So some notation to start with is that when we see A stroke B like this, then that's going in this section to mean A divides B. Simply that. And if we've got a situation where A divides B and A divides C, then A will divide B plus or minus C. Now this is going to look fairly innocuous, but and in fact just in A's B's it looks fairly strange. But if we have a look at that, so let's say 4 divides 12, and 4 also divides 8, whereas this first number stays the same. We're looking for two different factors, I suppose, not different factors, but different starting numbers. Then what this is saying is 4 will also divide B plus C, so that's 20, and 4 will divide B minus C, which is 4. So that checks out okay. Okay, another property is that if A divides B, and we also A divides BC, so if A divides B, then then A will divide BC for any integer C. Okay, so an example here would be, if 3 divides 12, then 3 is obviously going to divide 12 C, where C can be anything at all. So if we say therefore 3 will divide 12 times 2, so 3 divides 24, 3 divides 12 times 3, 3 divides 12 times 4, you get the idea. 3 will also go the other way and divide 12 times minus 1, 3 will divide 12 times minus 2, etc. Okay, now divisibility tests. These are fun. Now you will have struck these before quite a long time ago. Divisibility tests. Okay, so for divisibility by 2, then we just need the number to be even, so it ends in 2, 4, 6, 8, 0. Divisibility by 3, you might remember, is the sum of the digits is divisible by 3. Okay, by 4, then what do we say? That the last 2 digits of the number are divisible by 4. Divisible by 5, then we're going to ends in 0 or 5. That's a straightforward one. By 6, now this is therefore divisible by 2 and divisible by 3. By 7, we haven't got a divisibility test for 7, So I'll skip to 8 by 8. Okay, by 8 it's the last 3 digits. Divisible by 8. By 9, similar to 3 in that the sum of the digits divisible by 9. 10's easy, obviously ends in 0, and we stop at 11 by 11. Alternate, so this is where the alternating sum of the digits. Alternating sum of the digits is divisible by 11. So alternating sum meaning, so e.g. 209 is that divisible by, is 11 divisible by 209? I've just realised I've probably just written these the wrong way around, haven't I? So this is 3 divides the sum of the digits, so it should be 3. So what we should have here is 3 divides the sum of the digits. 4 divides the last 2. 5. Right, that don't need to write that. So that would just move those out the road. 8 divides the last 3 digits. 9 divides the sum of the digits. And finally 11 divides the alternating sum of the digits. So I was about to have a look at an example here of, say, 264. Then to test for divisibility by 11, we start with 2, we subtract 6, and we add 4. That equals 0, which does divide 11 0 times. So therefore 264 is divisible by 11. So just to get the order right there. Okay, so some divisibility tests. Now when it comes to proving some of these, what's going to be really useful is some notation around how to split the digits up. So I'll just pause and write this out. Okay, let me just explain what I've written here. If n is a k plus 1 digit number, so yeah, like a 6-digit number, say. If k is a 6-digit number, then let's look at a 6-digit number, 325,102. Then we write this number here as, right, that place value there is 10 to the 0, 10 to the 1, 10 square the hundreds, 10 cubed, 10 4. This is in 10 to the 5, so it would be 10 to the 5 times 3. That's 3 times, and this would be 10 to the 4 times 2. And this number here represents 10 cubed times 5, and this place value is 10 squared times 1, and this place value here is 10 times 0, and this place value here is just 10 to the 0, or 10 to the 0 times 2. So 1 times 2, 10 times 0. So this is 10 squared times 1, so it's 102. So if you put all that place value together, so if we've got a k plus 1 digit number, then we can write it in general form with these digits, ak minus 1. So these represents the actual digits. These a's are my 325102 here. And these 10 powers of 10 represent the place value. Now if we have a k plus 1 digit number, then this is how it pans out. Now it's k plus 1 because this last one here is 10 to the 0, so 0 through to k gives us k plus 1 terms, k plus 1 terms, k plus 1 places, therefore k plus 1 digits. Now if we break it, so we can write a number in this format, so that we're going to find that this is useful so that we're able eventually to split up these a's, which actually just represent the numbers 325102. So if we're looking for, say, the sum of these digits 3, 5, 10, 11, 13, we would say this is, we would say that 3 plus 2 plus 5 plus 1 plus 0 plus 2. And why do we want that? Because it's useful to find out the divisibility of a number. then we can, that's obviously 5, 10, 11, 13. But we could write this in A format as AK plus, plus AK minus 1, or in our case, because we know what K is, we can go back and we can fill in for K. We don't need to put in the, so we can say this is A 5 plus A 4 plus A3 plus A2 plus A1 plus A0, 1, 2, 3, 4, 5, 6-digit numbers starting with A5. So these are our numerical values, and the 10s give us our place values. So that gives us some scope to work some things through. Just have one more, a couple more bits of notation before we close here, and that is, alright, so for any integer, so this is all for exercise for section 2a. For any integer power n, and a useful result here, for any integer power n, we can say that a to the n minus b to the n has a factor, as a factor a minus b, and we can say that a to the n plus b to the n has a factor a plus b, and we know this from the difference of two squares, and we know this from our polynomial division that we did earlier in the core course. So that's going to be really useful for any integer power n. We've got that result there. And then finally, if I just change my color again, alright, if I know that a divides a number n, and also that b divides the same number n, and if a and b are what's called relatively prime, which means they have no common factors greater than 1, and if a and b are relatively prime, then we can say that AB, the product, will also divide n. Right, so if we have a look at a little example of this taking place, right, now we might say that 6 divides 18 and 9 divides 18, but they're not relatively prime. So actually, when we do 6 times 9, we get 54 divides 18, which is incorrect, and it's incorrect because they're not relatively prime, right? But if we look at an example where we do have relatively prime, 7 divides 14, we also know that 2 divides 14. It's 2 and 7 are relatively prime, so we can say that 14 divides 14, and that's all good. We might go for 4 divides 24, and we also know that 3 divides 24. 3 and 4 are relatively prime. They don't have any higher common factor than 1. We can therefore say that 4 3s are 12 divides 24. And this is quite useful to split up the other way. So if I want to, say, look at an example here, I think there's one in the book, if we have a look at, is, hold fire for a second. So there's a reference here to a divisibility. So we can do divisibility tests now by using any products of 2 through 11. So there's a question in question 2 of exercise 2a where you are we're testing divisibility by 36. So we're asking, does 36 go into these numbers? Well, we can find out two things. We can say for 36 we can use two relatively prime numbers, and they would be, so if I know that 9 goes into n and 4 goes into n, because 9 and 4 are relatively prime, and if that's the case, I will therefore know that 36 goes into n. So I can test a number for divisibility by 36 by using that. And if we continue that example, just looking at this number here, so for example, is 36, does 36 divide 82? I haven't worded that particularly well, have I? It's a sort of a bit of an afterthought. Is 820,836 divisible by 36. Right, another way of looking at that in shorthand is, or does 36 divide into 820, 836? All right. So we can go, oh, well, I don't really know. I don't have a divisibility test. I do not have a divisibility test for 36, but I do have one for 9, and I have one for 4. And I know that if 9 goes into it and 4 goes into it, they're relatively prime. 36 will go into it. So I can test. So I can say, does 9 go into 820, 836? All right, so I just add the digits, 8 plus 2 plus 0 plus 8 plus 3 plus 6, because that's my divisibility test for 9. It's the sum of the digits. Right, if the sum of the digits is divisible by 9, then I know that number is. So 8, 10, 18, 21, and 6 is 27, which is divisible by 9. So I give that a tick. I check 4. Does 4 divide into 820, 836? Well, then my divisibility test for 4 is just to check the last 2 digits, and that is a tick because 4 goes into 36. So therefore, because 9 and 4 do, 36 divides into 820, 836. All right, I'll let you go into exercise 2A. I'll put another YouTube up for the next section on greatest common divisor and least common multiple. For 2B, and we'll have a go at those questions in class.